All right, let's get started. So how many people are done with P4A? Okay, very good. For the rest of you, before I start talking about P4B, do you have any questions about P4A? Yeah?
So you want us to work with like condition variables and everything. Is there like a specific module that you want us to work with, or is there like should we just make our own, or they're not condition variables but like locks and things, right?
Yes.
What should we use for lock? Is there a pre-made lock, or should we?
Pthreads has condition variables, I think.
Oh, okay, guys.
So, you just use some library. Yeah, you don't have to make your own. Like,
oh yeah, I just wasn't sure of like the actual like where it was.
Okay. Any other questions? Yeah.
Are there sample midterms?
I'm sorry.
Do you have any sample midterms for that?
Sample midterms. So sample midterms are already. We posted a link, but basically, where we get them is from Ramsey's page. So let me see. So. There we go. So there's a whole bunch of like sample midterms with solutions. So those should be good practice for you. Okay. I think I did send out this link to the class mailing list, but I'll send it out again anyway.
Okay. So with those, there were only 2 exams per semester at that time.
Right.
So like, could you give like is it just going to be everything from the last midterm up until this one, just because it's not well broken down there?
Oh, okay. So basically, yes, we have everything from condition variables down until the fast file system.
Okay.
So that's going to be the total portions for our exam.
Thank you.
Okay. Any other questions? And some people had emailed about this. So basically, all the information about like exams and stuff will be in overview. So if you just scroll down, you can see that it's at 7 to 9 p.m. in chemistry 1351. So basically the same place we had our previous midterm. Okay. Okay. All right. So let's get started. We'll talk about P4B. So P4B basically makes you add kernel threads to xv6. Okay. So currently xv6 doesn't have any threads, and what you'll be doing is all the basic groundwork to add a very primitive implementation of threads to xv6. Okay. There will be like 4 system calls that you'll be supporting, and the first one is basically the meat of the whole thing. It's called clone. And what clone does is it creates a new thread with the stack that you currently pass to it. Okay, I'm not sure if you people remember, but like basically, your threads all share the same address space, but they all have their own stack. So when you're creating a new stack, when you're creating a new thread, what you do is you allocate some space for the stack, and then you pass it to the clone function. Okay, and the clone function sets up that space as the stack of the new thread, and then lets the new thread run from that stack. Okay, so that's basically the stack variable that you're seeing here. We'll talk about clone a little in more detail in a little bit, but lock and unlock are the basic things that you would expect. If you look at the x86 code at all, you know that there are already locks in the kernel. So what you'll have to do is just expose them to user space. It's going to be very easy. The lock implementation is a sleeping lock implementation, which basically means that if you try to acquire the lock, somebody else already has the lock, you go to sleep. And then when somebody unlocks, they wake up everyone who is waiting for that lock, and then a process runs. Okay? So why don't I just talk to you about those stuff first, and then we'll go and talk about like clone, because like those are the easy portions of the thing. All right, so let me just SSH. Staying a while. What network am I on? Okay. Should not take this long, huh? Okay. Anyway, so CS537 discussion. Today is 12, no 11. Okay. So what? Oh, it's switched to Java. Yeah. Well, we'll just work with this for now. Public. All right. Okay. So let's see. Let's get C tags up. And can you guys see? Can everybody see? Okay. All right. So you probably already know about, let's say, wake up. Okay. So if you go to proc.c, you already have functions which do sleep and wake up, right? So this is working on. So this function is basically working on like a particular channel, and our channels can be anything. Like we can give a spin lock or a condition there. So this will basically, if you give the state of a lock here, this will do all the work for you. So it will acquire the lock on the p table, then release the lock, and then it will wake up everyone who is waiting for that particular condition. Okay. Similarly, we also have the sleep function, right? So the sleep function, it already takes a spin lock, and then what it does is it atomically releases the lock and then goes to sleep on that channel. Okay, so it reacquires the lock when awakened. So these are all the primitives that you actually need to expose user space locks, lock and unlock. You just need to make sure that when you're getting a lock, you try to see if you have the lock. If you don't, you go to sleep. In unlock, you wake up someone who's already waiting for the lock. Okay. Does the idea of like what you should do in lock and unlock seem clear? Okay, because these are like the easy parts of the project. So you should do that like first. Okay. Okay. Hopefully you guys get that. All right. So we saw how to do, or like an intuition of how to do lock and unlock. Okay. So clone is going to be the meat of the thing, and then join is very similar to your wait function for processes, right? You create a child process and then you call wait, and then the parent is blocked until the child completes. So very similarly, you can create a number of threads and then you call join, and then the parent is waiting for the child threads to complete. Okay. So in order to do this, you will once again have to do something similar to what you already have in the kernel for wait. Okay, so you already have code which is waiting for a child process to exit and return its PID. Okay, so the core functionality is already in there. So much like P3B, most of this project will be understanding what is already in the kernel and then making very small modifications to make it work with threads. Okay, so you won't be writing a whole bunch of new code for this project, but rather understanding whole code and then seeing how to modify it. Okay. So, case in point, this is already doing pretty much what we want. It is looking at all the child processes, and then once it finds something that's zombie, then it's resetting everything for that child process. You'll have to do similar things for a thread. Okay? Let's see. So, sorry. That's how you do join. Then the user space function thread create is just like a wrapper for clone. Okay, so what does clone give you? The clone creates a new thread, and actually clone returns the thread ID. And so what it's basically doing is it's creating a new thread and with the stack that you give it. What thread create additionally does is it takes the new thread and it runs a new function on top of that with the given arguments. Okay, so if you think about it, this is going to be pretty much code like, well, let's do a different version, then maybe you'll understand. So if I said you had a similar function wherein you had to execute something in a child process, Okay, think about how you'd do that. You'd basically say, you'd fork, and you'd say if PID equals 0, then you just call function with that argument. Okay, so that's how you do it in a child process. It's going to be very similar in a child thread. Okay, it's not going to be significantly different in a child thread. So you don't have to think too much for this. So this will, yes?
So I'm just confused about like, the arguments with the thread created. Does that mean that it's like a void function that takes in a void pointer?
Yes. So basically, this is the most generic way in which you can write a function pointer. It can be cast to anything. So basically, you can actually send in a pointer to a function which actually does take arguments and it will still work because you can cast it and then pass it along. Okay. Just as in like how any argument can be cast as void a pointer and then back again without loss. So you can do a similar thing with void pointers. Okay. Okay. Oh yeah, and this is important. Okay, so you modified a lot of things for the P3B kernel. You don't have to do any of those modifications for this project. Start with just a clean x86 kernel. This means that you're going to just have like one page of user stack. That's fine. Okay, you don't have to relocate the stack. You don't have to grow the stack. You don't have to do anything like that. Just the normal stack as before is fine. Okay. All right, so now let's look at the meat of the thing, which is clone. Okay, so clone is just going to be a variation of fork. Okay, fork creates a child process. Clone is going to create a child thread. Okay, so the way I'd recommend you do this is you take fork and then you make a copy of it, and then you call it clone, and then you get that working initially. Okay. So your fork, whatever your fork is doing, you'll be editing that to make your clone. So you should start off from the fork code. Okay. So let's look at what fork is doing. The first thing it's doing is it's doing an alloc proc. Okay. Alloc proc just finds a slot in your p table which is unused. Okay. You guys should already know a lot of this material by now because you worked on P2, you worked on P3, so you already know what the P table is, you already know what it means when it says the state is unused. Okay, there's a slot in the P table where there's no process, so we're going to use that for our new process. When implementing this project, one way you could possibly do this is to have a thread table like a process table, like a P table. Okay, but you actually don't need to do anything like that. Just use slots in the process table for your threads. Okay, so there's going to be like 64 different threads in the system. Okay, that's going to be the maximum because like that's how many processes we can have. Okay, so you don't need to differentiate between your process and your thread at this level. So let's see. So it's setting the state as an embryo, it's getting the ID as the next PID. This is totally fine. All your threads can have different PIDs. Okay. It's allocating the kernel stack. All right. Let's see if people actually understood this. So should a thread have its own kernel stack or not? So okay, if you're asking what a kernel stack is, I suppose this question is irrelevant. But if you guys remember from way before when we did P1, there's actually two stacks for every process in the system. One is called a kernel stack, another is called a user stack. The user stack is where when you call different functions, you put those arguments for those functions on that user stack, and the return value for that function is also put on the user stack. So that's how you put arguments in, you do computations, and then you pop arguments out to get the return value. Okay, so that's what your user stack is used for. Your kernel stack, on the other hand, is going to be used to save your trap frame. Do people remember what a trap frame is? Yes? No? No recognition? Okay. Okay, you should actually somewhat know what a trap frame is because you people would have done something like this for P3B. Okay, so your stack pointer is actually part of your trap frame. So the TF here in this code is actually your trap frame. So when you're doing a context switch and when you're calling into the kernel, for example, everything that is currently your stack pointer, your instruction pointer, your program counter, all of that needs to be saved, right? And where is it going to be saved? It's saved in your trap frame. Okay, so that contains all of the details that you need to suspend execution and to resume execution. Okay, your trap frame is going to be stored in your kernel stack. So that's why we have a kernel stack. Okay. Now, coming back to my original question, should threads have their own kernel stack? And if so, why?
I think so, because they're going to have different instruction pointers and they're going to have different stack pointers as well.
Correct. Your threads are like units of execution, right? They will have their own stack, which means they have their own stack pointer. They're going to be executing different points of code. All of that is tracked in your trap frame. So every time you have a kernel thread, you do need its own trap frame, which means you do need its own kernel stack. So coming back, in alloc proc, it creates its own kernel stack. Please do not switch this off. Okay, I can already see that this is going to be one source of error. People switch off the kernel stack. I haven't played around with this, with turning off the kernel stack and seeing what will go wrong, but it will not be anything good. Okay, so there will be weird errors and it will be tough to debug. So don't turn off the kernel stack. Okay, let's see, what else are they doing? So they're just setting it up so that your new process returns from the fork return and from trap return and so on. Again, this is if you remember from P1, you do a chain of things when you create a new process and you go to different steps in the kernel before you come back out to user space. So you go to trap.c and from there you go to all traps.sim and so on and so forth. So this is doing all that work. Okay? So I mean, another way of saying this is you don't need to modify any of this. This is all like standard return from kernel stuff. Okay? So the high level point is don't change alloc proc. Okay. Let's see. So, what about line 138? Should we? What's it doing? Let's go from there. What is line 138 doing? For people who did P3B, they should know this. Yes.
It's copying the page directory from the original process into the new process. Like
Oh.
it's creating a memory for it.
Okay. That is correct, but like a little more detail. So
So it's copying like, yeah, all the code, the heap, and all that into the
Yes.
process.
exactly. So if you go look at copy UVM, which you should have for your project, look at what it's doing, right? It's basically saying I'm going to copy everything from size 0 to whatever is the size of the process, page by page. And I'm going to set up, or I'm going to copy all of these things from one place to another. I'm going to check that it's physically present, that it's paged in and all that. Okay. Now, it's copying all of this from the NP is the new process, proc is the old process. So it's copying all of this from the process to the new process. Okay, so should we do this for our threads or not?
No,
Yes.
because the code and the heap are the same, like they're shared.
Correct. That's exactly what it means. We are sharing our address space. Okay, address spaces are shared between threads. Now you learned this in class in a very sort of abstract way. This is actually physically how it is done. Okay, so here we are saying that we are going to copy over all of our virtual memory from our process to our new process. Okay, it's creating a copy UVM. Okay, here we don't want to do that. We actually want the exact same address space. Okay, so all of this is just going to be replaced in your clone implementation by saying the new process page directory is going to be the old process page directory. Okay, of course you'll have to do more work, but that's a starting point. Okay, because your code is going to be the same, your heap is going to be the same, but one thing is going to be different and you will have to handle that. Okay, they have different stacks, so you'll have to make sure that you handle that correctly. So one thing that was useful while I was doing this is we have a link to PDF in the project website, and it's basically a free book which talks about x86 calling convention. Okay, as you might have figured out by now, to do this project, you really need to understand how stacks work. Okay, I mean, the intellectual meat of the project is basically setting up a new thread, setting up a stack, and making it run on that stack. Okay, so it will help if you understand how it is that we are using the stack in different programs. Okay, so there's a chapter 4 in this book, and it basically tells you all about the x86 convention. So it shows you sample programs, for example, and it shows you how we do push things onto the stack, how we call functions, how we return from them, and so on. Okay, and it's very written in a very clear way. So for example, at each step they'll show you what the base pointer is at, what the stack pointer is at, and so on. Okay, and the reason I'm telling you to go read all this is because when you set up a new stack for your kernel thread, you will have to set up your base pointer and stack pointer. Remember that they're previously pointing to the old stack, the process that called clone, right? So let's say that the old stack is at address 1000 and the new stack is at address 2000, right? You need to change the thread's stack pointer and base pointer so that they point to something around 2000 and not something around 1000. Okay, does this make sense? So okay, so you have your old process and you have your kernel thread. Okay, so when you do clone, you're not changing the address space at all. They're both going to share the same address space. Your new kernel thread has a new stack, okay, which you allocate and you pass into clone, if you remember from our thing. Okay, so you pass in the address of the new stack to clone. Okay, now it's not enough if you have just some allocated space which is called the stack. It has to be correctly pointed to so that programs can use it, right? So for that you need to set up the stack pointer and the base pointer. Okay, so you will have to go look at like how this is done in x86, and then you have to do something similar to get your new kernel thread running with your stack. Okay, basically you'll need to understand when a thread is created, where should the base pointer point to, where should the stack pointer point to. Okay, so that's basically what you want to do. So this will be a good resource. Let me see. Okay, the rest of the stuff is just like it copies over the current working directory, the files, the PID number, which is something that we don't want, and it makes it runnable and then copies the name. Okay, so all of this is like pretty standard stuff. You wouldn't have to change it. This project is very related to P3B in that you have to keep in your head where is the code, the heap, and the stack. Okay, and then you'll have to make sure that in the new thread, these are all pointing to things correctly. Okay. Okay. Let me see. Clone thread create. Okay. I've already told you how join is supposed to work. You just wait for all of your child threads to finish. Very similar to your current wait code. So copy that code and modify it. Okay. Okay, so one other thing that I noticed while you guys were doing P3B is that you try to do things incrementally. You basically change one thing out of step of 10 and then like you see whether that works. So when you're doing kernel programming, you can do that, but you have to be prepared to be frustrated for a really long time. Okay, so if you have 10 steps and at the 10th step your clone works, you need to get all 10 steps to work before it will stop crashing. Okay, so through steps 1 to 9, it will crash and it will give a different bug each time. So that's actually a clue for you to go and figure out like what you have to do next. Okay, so I had a lot of students who were like very frustrated that like I keep doing changes and then it still keeps crashing and like they were very sad. It's totally expected. That is in fact how kernel programming is supposed to work. You can do this in two ways. You can figure out everything that you need to do correctly and then go do it at one shot and that will work. But unfortunately, we don't program like that. So every time you do an incremental change, it will crash. Be prepared for that. You have to get good at reading what the different panics are. Okay, so if you really look at it, your panic actually tells you enough information to figure out like what's going wrong. Look at what panic is saying, what was happening before you hit that panic, put a lot of panics in your code, and then use that to debug. Okay, and don't worry if it crashes. It will keep crashing until the last time, and then it will work flawlessly. Okay. How many people know how to do XV6 with GDB? 1, 2, 2. Okay. So it turns out this is actually really helpful if you run XV6 with GDB, because basically every time you hit a panic, there are two ways to debug with that. Okay, one, you can put a lot of printfs everywhere, so that when you hit a panic, you can see what all printfs were triggered, and so you know what led to that panic. Okay, another way to do this is have a lot of panics, and then in GDB you put a breakpoint near your panic, and then you do a backtrace. Okay, do you guys want me to demonstrate that? Would people be interested? Okay, so let's go do that. Okay, so we have our XP6. So the first thing to do is we set up another window. Okay, so CS537 discussion. My wrong naming. Okay, so you guys already know about make QEMU Nox. So there's a version called make QEMU Nox GDB. Okay, so now what we do is in the same directory. Okay, this is important. In the same directory that you have the other code where it's like you're running QEMU Nox GDB, you run GDB, and sometimes it tells you an error like you have to add a certain file to your GDB init. Okay. So what this is basically telling you is CSL has some restrictions on where you can run GDB successfully, okay, for security purposes, because you don't want GDB running on different processes. So so because of that, we actually have to set it up so that we can run GDB successfully in any given directory. And the thing to do is very simple, okay. So wait. It will tell you what to add. Oh, sorry. Okay. So as you can see, I've already added 2 different directories there. So for example, projects P3B and discussion 0923 are already directories in which I can run GDB successfully. So I'm just adding this current directory to that. Okay. So I just add that, and then I say GDB again, and this time it doesn't give me any errors. Okay. So now if I say continue, my kernel runs in the other window. Okay. So you can control the execution of that from here. So you can say something like, let's say we want to do a break at fork. Okay. So it says that we have set up a breakpoint in kernel proc.c at that function. Okay. So now if we say continue, okay. So this is running. If I'm trying to do ls, this will call fork. If people remember, your shell forks a new process, right? So then this will stop because control has passed here, and then it says we have hit that breakpoint. Okay. Sorry. Okay. So it says we have hit that particular breakpoint, and then what we can do is, and this is the most useful part, we can do something called backtrace. Okay. And what backtrace does is, it tells you what functions were called before we hit that particular breakpoint. Okay, so in this case, as you already know, I called ls from user space, that leads to a trap. From the trap, we find out that it is a trap for a system call, that calls sys.fork, which calls our function. Okay, so using GDB is a really easy way to understand what's going on in your code. Okay. So every time you do something like this, you can figure out like what is going wrong, and you can actually look at different frames. Okay, so let's go look at frame 2. Okay, so what it is saying is that in frame 2, which is like here, this is what was actually getting called. Okay, so we are calling our system calls of number with whatever is the number for fork, and then the return value will be in EAX. Okay, So this is all stuff that I've shown you before in sort of a P1. But this is another way of looking at the same thing, at what is going on. In fact, we can also do things like print num. Okay. So num is actually whatever was the value of num here when this was being called. Okay. Let me see. Print proc trap frame. Okay. Oh, it doesn't see that yet. Let me see. Print syscalls. So you can look at the different tables that are there, and you can see that sys4 is actually number 1. Okay, so that's why we got num1 when we did that. So we're actually calling in the first function that is present in the table. Okay, so this is really sort of like incredibly useful when you want to do debugging, because you can see from where you ended up at this point, and you can go to each of those points and you can see what was being called before you ended up here. Okay, and it really helps when you are doing all sorts of like weird stuff in the kernel and you're not sure where variables are getting changed. Yes?
Why can't you access the proc structure then?
So your variables need to be in scope for it to work. So your current frame is where was that? So it's currently executing this stuff. Okay. So that means that it's able to see some variables but not others. So the proc thing is not in scope. I'm not sure exactly why it's not in scope at this point, but
It's global across the kernel as far as I know. It always contains the running process.
correct. That's true, but that is different from saying it's in scope. Okay. How do I explain this? You know how in C you have scope similar to how like if you open a new block with like brackets, it's visible only within that scope, right? So this is similar to that. It has nothing to do with global variables. So every time you call a function, certain variables are in scope and certain variables are not. So it's just that at this point, GDB it cannot see the proc variable. I'm sure that once we finish execution, right? We have just started executing this. We haven't actually executed this line yet. Okay, so when we finish executing and we come to this line, proc will be visible again. Does it make sense? So if you look at this as assembly, okay, this part of it is what is executing. That will be put in this part. Okay, so this is not visible yet. So that's also going on. Any other questions? Yeah.
Yeah, you said for new thread we need a new stack, but I just wonder, is there any requirement for where we should put the new stack for new thread?
No, you just like okay. So you just call malloc and then you get a new page and you can pass that in. Okay. Remember that your clone is going to be called from user space, right? Okay, which means that you are allocating a page for your stack and you're just passing that value in. Okay, you could do that in your stack, but your stack is just one page, so you can't really allocate the whole page for another thread stack. Am I making sense? You only have two places where you can put the new stack, right? You can put it in your stack as part of your stack, or you can put it as part of your heap, right? Okay, your stack is already just one page, so allocating a one page size stack is going to be a problem. So you allocate it in your heap. Okay.
In the old press heap?
In the what?
In the
Yes, in your parent processes heap. Yes.
Okay, so you're gonna grow the heap.
We are going to grow the heap. Correct. Okay. Yes.
Would it let the parent access the child's stack?
Yes, that's true. Yeah, we don't need to worry about that here. But you do raise an interesting point though. So if you look at, I don't remember where it was, but let's see. So this is the function for growing your heap, okay, as you guys would have found out. Now, this is okay currently because there is only one process which is accessing the heap at any point of time. Okay. Once you have threads, remember that your heap is shared between threads. So there will be multiple guys calling grow proc at the same time. Okay, which once again means that you will need to have some protection in grow proc. You can't all grow the heap at the same time. There has to be a lock somewhere. Okay, so in part you have to be really careful about assumptions like this in different parts of the code. Okay, think about where it would be a problem if multiple threads are accessing the same code. Okay, I can show you another place where it will be a problem. Okay. Oh, not here. So let me see. Okay, so this is the implementation of the wait system call. Okay, and look at what it's doing. So let's assume that a parent process created a child process. Okay, and then the child process is done. When it exits, it goes into zombie state, and then the parent can actually free up all the space. Correct? Now, part of what they're doing is free VM, which means they're freeing everything in your page directory. Okay, this is okay if it's a process. This is very bad if it's a thread, because we're all the threads are sharing the same page directory. So if one of your threads calls free VM, then all the threads are gonna die. Okay, so you will have to be careful about things like this in your code, like because if multiple threads call this, it's going to be a problem. You have to make sure you have to protect that. Okay, you should only call this freeing of the page directory when there is no other thread which is accessing the same page directory. Okay, there are a number of like nice ways and hacky ways to do this. One hacky way is all of your threads will have the same pointer. You can just go through the process table and then compare with the current pointer that you have. See if anybody else has the same pointer. If they do, you don't free it. Otherwise, you do. Okay, very simple hacky way to do it. The sort of interesting and nice way to do it is you reference count your page directory. Okay, so when a process is created, the page directory has a reference count of 1. Every time you create a thread, the reference count is incremented. Every time you find a zombie child thread that has finished, you decrement the reference count. When it drops to 1, you know that there's only one guy who's accessing the address space, and then you can kill it. Okay? Questions? Yeah.
So when you say when you said that you malloc space for the stack,
Yeah.
so you don't use malloc function. You use the grow proc, right? Because you cannot use malloc in the kernel space.
No, I'm saying. Okay. So basically, you will call clone from your user space. Okay. Which means that at this point you don't have access to grow proc. You only have access to malloc. This is still in user space.
Okay.
Okay. So you have to use malloc, which internally we'll call grow proc. Okay. Yeah.
What happens if the parent ends, but the child is still running?
What happens
So
with the?
you have a program. Let's say the shell is forking a process,
Okay.
and that process is creating a child thread,
Okay.
and the parent process ends.
Okay.
So should we? So the way at least in x86 it works is when a process ends, it goes into zombie state, and
Correct.
then its parent calls wait and cleans it up.
Correct.
Right. In this case, you're going to have should the thread's parent be shell, or should it be the process?
So this is part of the extra credit. So you can basically see that when a parent exits without calling wait, the child process is left in a zombie state. Okay, so that's how it currently works. And then the init program collects all those zombie things. It frees them. Okay, so that you can modify it so that it also collects zombie threads. But this is extra credit, and you don't need to do it for the normal project. Okay. Other questions? Yeah.
So is it okay if like different threads access each other's stack, so we don't have to worry about that? Like Like
If you're asking about security, yeah, you don't have to worry about security. But if you're asking about like, well, I don't know what you're asking about then.
like if you create new threads and you're gonna call like malloc multiple times,
Okay.
and like every thread will have its own like one page text space.
Correct.
So we don't have to do anything like if one thread, like if one process is trying to access some other process.
Yeah, you don't have to have additional safeguards in there so that that doesn't happen. Yeah, you can assume that your programs are well behaved. Yeah. Other questions? Okay, I think we'll wrap it up for today then. I suggest you all get started on this like really quickly because it's a detailed project. The thing is simple once you understand it, but you still need to take care of so many details to get it right. Okay? All right, thank you.